Good afternoon. Thank you all for coming. I definitely did not get a large enough room for this. I'm really excited to talk with you all about the work that I've been doing during my dissertation, and in particular for those of you who are at the thesis proposal, I'm going to be really focusing on the work which has taken place since the proposal. The field of reinforcement learning has seen several attention-grabbing successes, many attention-grabbing successes in the past few years. There's been a lot of exciting progress. So actually the first result that I'm showing here, superhuman performance at Atari video game playing. This was done just as I was beginning my PhD. But then a year or so after that, superhuman performance at the game of Go from UT Austin. Simulated robots that could learn how to run, kick soccer balls, and all the skills needed to play soccer. And there's been applications not just to games, but also in industry. Tasks such as web marketing, control of data centers, or control of home thermostat systems, where reinforcement learning has been shown to be effective. But if we look a bit more closely at these results, we can see that while reinforcement learning is effective, it's not always efficient. So in this Atari video game playing, the agent had to try 50 million actions before it had a good policy for the task. The game of Go, 21 days of the computer playing millions and millions of games against itself. And as one more example, these simulated robots took 1.5 years of compute time to learn all of the skills necessary to play soccer. And so I think these results have raised the question for many people in academia and industry of can reinforcement learning be data efficient enough for real-world applications? So my dissertation was motivated by this question, and I focus on two limitations that many reinforcement learning algorithms currently have. So these limitations are first that many algorithms need to be what we can call on policy. And I'm using this term somewhat loosely, but in the strictest sense, on policy means that the algorithm can only use data generated by its current policy or a policy of interest. And so I am using that term somewhat loosely, but in general, many algorithms rely on using data that's from a policy that's similar to their current policy, even if it's not the exact one. And the other limitation that this dissertation addresses is that many reinforcement learning algorithms need to be what we call on environment, meaning that they must learn in their target environment of interest. This problem is especially felt in robotics, where we may have access to good simulators that model the world well, but inevitably, if we apply reinforcement learning in simulation, we cannot expect what we learn to transfer onto the task of interest. So towards addressing this big question of making reinforcement learning more data efficient for real-world applications, my dissertation tries to answer answers this thesis question: how can a reinforcement learning agent leverage off policy and simulated data to both evaluate and improve upon the expected performance of a policy? We answer this question by answering 4 smaller questions. These questions are: how should a reinforcement learning agent collect off-policy data? How should a reinforcement learning agent weight its collected off-policy data? How can a reinforcement learning agent use simulated data? And finally, how can a reinforcement learning agent combine both simulated and off-policy data? So I'm not going to talk about all of these in depth today. They're covered in the dissertation document, and I'm happy to take questions about them. But before talking about any of them, I want to present a bit of background on reinforcement learning, just as a way for me to state some of the assumptions I make, or for members of the audience who are less familiar to understand the formalism. Reinforcement learning models an agent interacting with an unknown environment. The agent's behavior is captured by what we call its policy and denote with the symbol pi throughout the talk. And in general, what pi is it's a mapping from any state of the world to a probability distribution over possible actions that the agent can take. So given a policy, the agent interacts with the world as follows. The agent begins in some initial state. It takes an action according to its policy. It receives a reward for doing so, and then the environment transitions to a new state. And this process repeats for a fixed number of time steps. We call this entire sequence of interaction a trajectory. After a trajectory is complete, the agent can go back to an initial state and start the task again. Now in reinforcement learning, there's 2 problems which are that this dissertation looks at. The first one, which most people associate as being the ultimate goal of reinforcement learning, is that of policy improvement. We want to find the policy which maximizes the expected reward total that we'll receive when we run it in the environment. But a second problem, which is at least as important, if not more important, is that of policy value estimation, where we're just given a fixed policy, and we want to determine the expected cumulative reward that we will receive when we run that policy. And so the reason that I think this problem is at least as important as policy improvement is, first of all, many policy improvement algorithms rely on good value estimation to do the policy improvement. And second, for any application where we're considered with the safety of deployed policies, it's going to be necessary to be able to quickly and efficiently evaluate what's going to happen when we run a particular policy in the world. So much of my dissertation work focuses on the policy value estimation question. And I want to just mention here that I call this problem policy value estimation to distinguish from the related problem of policy evaluation, or trying to learn a value function, which is also commonly studied in the reinforcement learning literature. So policy evaluation, more specifically, we're given a fixed policy that we call the evaluation policy, and we want to know when we run this, what is the reward total that we should expect to receive per trajectory. And what we want, the solution to policy value estimation is we want to come up with estimation techniques which allow us to accurately estimate this value. The objective that we seek to minimize is the mean squared error, where if we have some estimate of policy value, we want in expectation for that estimate to be close to the true value of our policy. So one of the simplest ways to tackle policy value estimation is to just run the evaluation policy and see what happens. So this is called Monte Carlo value estimation. So you can run the policy, generate some large number of trajectories, and then just average the reward seen. And this will give you an estimate of the policy's value, and as you generate more and more trajectories, your estimate will become more and more accurate. So this is a very straightforward approach, but I actually want to kind of illustrate what it's doing, as it's going to relate to later parts of the talk. So we have our true unknown value that we're trying to estimate, and we have a sample average, which is estimating it. Imagine a toy environment where we have 3 possible trajectories. Our evaluation policy and the environment in which we're running it induce a distribution over these trajectories. So we're going to see each of them with some probability. The Monte Carlo value estimate is going to sample trajectories from this distribution. And as the number of trajectories increases, we're going to see them in a sample proportion which is going to approximate the true distribution of them. And as m gets really large, this sample proportion is going to converge to the true policy of each trajectory, and our estimate will converge to the correct value. So this is you only will converge to the correct value if you're sampling trajectories from the evaluation policy in the target environment of interest. So one problem that we see in reinforcement learning is that of distribution shift. If we cannot sample from this particular distribution of trajectories, then we're not going to be able to do effective policy value estimation. Distribution shift in reinforcement learning can arise in 2 ways that we consider in this dissertation. First of all, our policy could change. So if instead of running the evaluation policy, we run a different policy that we will call the behavior policy, then we're now going to have off-policy data. And if our environment changes, for instance, when we're using a simulator in place of the true environment, then we're going to have simulated data which also comes from a different trajectory distribution. So returning to the toy example, if we're running a different behavior policy, then no matter how many samples we collect, our samples we're never going to converge to a proportion which matches the true distribution of interest. Shown here on this plot, that would be the red. Instead, we're going to be getting closer to the blue bars. So one way very simple way to address this problem is using importance sampling. With importance sampling, you can run any policy that you want to collect your data. But because the policy is different than the evaluation policy that you're interested in, you need to reweight the rewards which are received. So if you're not already familiar with importance sampling, it's not important to understand exactly how this reweighting is done. But intuitively, what we're saying is that if a certain trajectory is more likely under the evaluation policy than the behavior policy that generated that trajectory, increase the weight on it. and if it's less likely, then we want to decrease the weight. Once this reweighting has been done, we can average the reweighted rewards and use the data as if it had come from our evaluation policy that we're interested in. So again, in this toy example, even though as we sample from the behavior policy, our trajectory, the sample proportion is never going to be that of the evaluation probability policy, but because we're applying these reweighting factors, it doesn't matter. We can still get a good estimate of the policy's value. So with that background, I'm now going to dive into the contributions of this dissertation. And for most of them, I'm going to talk about them relatively briefly. And I'm going to start with the question of how should a reinforcement learning agent collect data for off-policy value estimation. So I talked about this a lot at the time of my thesis proposal, which is how should we collect off-policy data. And what we're meaning there at a more technical level is how do we choose the behavior policy for an important sampling policy value estimation. The choice of behavior policy is critical as it will determine the variance of this estimate. And we think before this work, the prevailing wisdom would have been that using the evaluation policy as the behavior policy would be the optimal thing to do. However, in fact, the dissertation discusses how this is not in fact the case. So the first contribution of this dissertation is that we formulate what we call the behavior policy search problem, which searches for a behavior policy which makes important sampling perform better. And we introduce the behavior policy gradient algorithm as the first solution algorithm for this problem. Now, since the thesis proposal, we've also done some work as an initial study of applying the behavior policy gradient algorithm to the problem of policy improvement. And I'm not going to talk about that today, but I'd be happy to discuss more about this work. So the main takeaway for the question of how to collect off-policy data is that being off-policy can actually improve upon being on-policy if you choose the behavior policy correctly. And this dissertation has introduced a method which will find a better behavior policy for important sampling. So that's all I'm going to talk about for now on this question of collecting off-policy data. I'm going to spend most of the time talking today on how should a reinforcement learning agent weight off-policy experience. So the question of how to weight off-policy data amounts to how do we correct for the distribution shift we see when we run a different policy than our evaluation policy that we're interested in. Important sampling is a very standard technique for doing this. So in some sense, we're asking, is there a better method than important sampling for correcting distribution shift? And the answer to that is yes. And we show this in several contributions made in this dissertation. First, we're going to introduce a family of estimators that we call regression important sampling estimators, and show that they improve on the standard important sampling estimator that I introduced a few slides ago. This improvement is based on the principle of being able to correct what we call sampling error. And we're going to take that same principle and apply it in policy improvement, and we're going to introduce what we call the sampling error corrected policy gradient estimator, and use this to speed up policy gradient reinforcement learning. Before getting into our contributions, I do want to take you all back to proposal time and talk about what I discussed there along this direction. So the problem that I proposed to tackle was that of important sampling with an unknown behavior policy. You can notice here that if you do not know what the behavior policy is that generated your data, then there's no way to compute these importance weights because you need the denominator to compute this ratio. So this is a really unfortunate limitation, particularly if you're working with data that was generated by a human and you can't just write down the PDF that was in the person's head when they generated the data, or your data came from some other source where you don't know the behavior policy. A really straightforward baseline for attacking this problem is to use maximum likelihood behavior policy estimation. You just look at your data, you use the policy that looks most likely to have generated the data. This is essentially a supervised learning problem. And then you plug that estimated behavior policy in as the denominator in your importance sampling ratio. So at the time of the proposal, was considering using, wanted to study how much worse was it using the estimated behavior policy than the true behavior policy. And maybe hoping to derive some theoretical bounds on how bad it could be and give practical advice on how to best estimate the behavior policy in practice. So it turns out that this was incorrect. and in fact that estimating the behavior policy is preferable to using the true behavior policy for importance sampling. So I'm going to show one empirical result of this before talking more about our contributions. This is from OpenAI's RoboSchool Hopper domain, so reinforcement learning benchmark for continuous control. The y-axis is showing mean squared error, so lower is better. Using the true behavior policy for off-policy value estimation does this well, but if you replace the true behavior policy with its empirical estimate, you can do much better. We're not the first ones to have noted that using the estimated behavior policy can improve on using the true one. And some of this work we discussed at proposal time as well. But in the causal inference and bandit literature, it's been shown that what's called estimated propensity scores can improve importance sampling. And in some work parallel to our own, contextual bandits, it's been shown that it can be optimal to use an estimated behavior policy. But our work stands out in that we're the first to show using an estimated behavior policy improves in multi-step environments such as Markov decision processes. So just to recall really quick the problem we're tackling, policy value estimation, we're given a fixed amount of data in the form of trajectories. So we say that we have M state action reward trajectories of L time steps each. We're given a stochastic evaluation policy, and we want to estimate what is the expected sum of rewards we would get if we ran this policy in our target environment. As I mentioned earlier, ordinary importance sampling is a method which is commonly used to tackle this problem. And what's important to see here is that this ordinary importance sampling is reweighting returns, and it's doing it in a way which corrects from the distribution of trajectories seen when running the behavior policy to the distribution of trajectories seen when running the evaluation policy. So this is a really nice correction. It has some nice properties. It's an unbiased estimator of the value of the policy. The downside is that it may take a long time to converge, meaning that the number of trajectories we need to observe may be very high before we can get a good estimate of policy value. So our proposed family of estimators is a relatively simple change to ordinary importance sampling. Specifically, we take the denominator in the importance sampling ratio and we replace the true behavior policy with a maximum likelihood estimate of the behavior policy. We call this maximum likelihood estimate the empirical policy. And one thing I just want to point out for now, although I'm not going to discuss it in detail until a bit later, is that we're introducing a family of estimators, where the family is defined by a parameter n, which means when we estimate the behavior policy, how much past history do we want to condition on when doing that? So when n is equal to 0, we're estimating what is called a Markovian behavior policy. It just conditions on the immediate preceding state. As n increases, we condition on more past states and actions. So what's important here is that by using the empirical policy in the denominator, we're no longer correcting from the distribution of the behavior policy to the distribution of the evaluation policy. We're instead correcting from the empirical distribution of samples to the evaluation distribution of samples. I'm going to talk about what that means, returning to this toy example that I introduced earlier. We have three possible trajectories. We're sampling trajectories by following the behavior policy, so according to these blue probability, the blue bars, and we want to evaluate these as if the trajectories had come from these red bars. Ordinary importance sampling is effectively correcting from the distribution of the blue bars to the red bars. But when we replace the true behavior policy with the empirical policy, we're now correcting from the sample proportion towards the evaluation policy. So for any fixed amount of data that we have, no matter what the sample proportion is, we can correct exactly back to our evaluation policy of interest. So what we say that the difference between the sample proportion and what we're sampling from, we call sampling error. And so no matter how much sampling error there is, regression importance sampling can correct from it to obtain a more accurate estimate. Whereas ordinary importance sampling needs to wait until it's observed, needs to actually observe samples at their expected proportion. So using the estimated behavior policy, I'm now going to show some empirical results showing how this improves performance. So this is on a grid world domain with discrete states and actions. The y-axis is mean squared error, so lower is better. The x-axis is how much data we've collected. So we want to be as low as possible with as little data collected as possible. Using the true behavior policy with ordinary importance sampling, we do this well, but if we replace the true behavior policy with its estimate, we do better. And there are other ways to improve ordinary importance sampling, but these techniques are more or less orthogonal to the work we're doing. So weighted importance sampling or normalized importance sampling is another alternative, but if you do it with an estimated behavior policy, you can further improve. And the same goes for the state-of-the-art weighted doubly robust estimator, which was introduced a couple years ago. This isn't just for discrete states and actions. On a continuous state and action environment where we use linear regression to estimate the behavior policy, here is using the true behavior policy. The estimate improves, and the same goes for per decision importance sampling, and to a lesser extent, weighted importance sampling. The next empirical result I'm going to briefly talk about is the fact that we're introducing a family of estimators. And the family relates to how much history do we want to condition on when we estimate the empirical policy. So as it turns out, conditioning on more history makes our estimator closer to a method from another literature which has some nice theoretical properties. So if we're using the true behavior policy, we do this well. If we use an estimate that just conditions on the preceding state, we do better. As we condition on more history, we see that the estimators do worse when there is very little data, but asymptotically they converge to a orders of magnitude better estimate of the policy's value. And what's really interesting is that there's a method from the bandit literature that in fact cannot be, in many realistic settings, could not be implemented for Markov decision processes. But for this very simple environment that we tested it on, we could implement it. And we show that our methods are actually approximating this method, which in some, along some axes was shown to be theoretically optimal. The next thing I want to talk about is that this is not just for off-policy data. We actually, if we make the behavior policy and the evaluation policy the same, we're seeing the same improvement. And the reason for this is that any method which performs Monte Carlo sampling in the action space of the policy may suffer from sampling error, meaning that the empirical distribution doesn't match the expected distribution of actions taken. And if we do know the desired action probabilities, as we do when we know the evaluation policy, we can potentially correct for the sampling error. And this naturally raises the question of, are there other reinforcement learning algorithms that could be improved by correcting sampling error? This leads to the fourth contribution of my dissertation, which is the sampling error corrected policy gradient estimator. And we're going to show how this can improve upon policy, make policy improvement algorithms more efficient. So let me give some quick background on policy gradient reinforcement learning. Intuitively, if you imagine all the space of all possible policies that our agent could run along the x-axis of this plot, and the y-axis is showing the policy value, so how policy performance for each of the policies. This curve is is the value of a policy, and I'm expressing this slightly different but equivalent to what I introduced earlier. This is an expectation over states from the policy's distribution, actions taken from the policy, and Q of SA says how much reward should we expect to receive after taking action A in state S. So this is another way of expressing how good a policy is. It's equivalent to the definition I gave earlier. Since we have an objective that we want to maximize, one really simple approach to this is to just compute a gradient of our objective with respect to policy parameters, which are denoted theta. We then take a step along that gradient, and we're moving towards an improved policy, which will give us more reward. Of course, in practice, we can't actually analytically compute this gradient, and so it has to be estimated. Typical approaches to this estimation use Monte Carlo sampling. So they run the policy and collect some batch of state action pairs, and then they can use this estimate by just averaging what they see. So this approach is fine. Like once, if the sample size is large enough, we're going to converge to the right answer, and we'll get a good direction for how to update our policy. The problem, of course, arises when our sample, when we don't have a large amount of data. Before going on, I do want to just expand upon the definition of what we're actually trying to estimate here, as it's going to maybe give some intuition for what we do next. So the gradient, expanding using the definition of expectation of what the gradient is, we have the inner gradient terms, and each is weighted by the probability of being in a state when following our policy and the probability of taking an action when in that particular state when following our policy. The probability of being in a particular state is unknown to us, but the probability of taking an action when following the policy is known to us. But I want to point out here that Monte Carlo style approximations to the gradient use sampling to approximate both of these probabilities, even though the inner one is known to us. So before going on to our contribution, this gradient estimation can be plugged into an algorithm. I'm going to give just the simple framework for policy gradient RL. Most algorithms look something of the following, where we execute the current policy for some number of steps. We then update our policy using the Monte Carlo average estimate of the gradient, and then throw away the observed data and repeat the process. And this is a simplification in some respects, but it's reflective of many state-of-the-art reinforcement learning algorithms, such as proximal policy optimization. So the reliance of policy gradient RL on Monte Carlo sampling means that the algorithm may suffer from what we call sampling error. This can lead to inaccurate gradient estimation and thus slow learning. One way to view this sampling error is that our observed data may appear as if it's come from a different policy than the policy we're actually interested in. If you consider this robot has a choice of 2 actions with some different probability for each, but it only takes a finite amount of actions, the proportion that it sees each action will in general not match the the probability that it took each action with. Which means for a finite amount of data, it may appear as if our data had been generated by a different policy. Of course, with enough experience, eventually these sample proportions will converge to the true probabilities, but for a finite amount, they will be different and will have inaccurate gradient estimation. So we take this view and use it to correct sampling error. We first pretend that our data was generated by the policy which most closely matches the observed data. We can determine this policy with maximum likelihood estimation, finding the policy which looks like it generated the data. In many reinforcement learning problems, this is essentially a supervised learning problem. Once we've recovered the empirical policy, we can use it to correct the weighting on every state-action pair to make it better match the weighting that we wanted to see under the policy that took these actions. So we introduced the sampling error corrected policy gradient estimator. It's essentially the same as the Monte Carlo policy gradient estimator. We're just adding an important sampling correction, which corrects from the empirical policy the way our samples actually fell to the current policy that we wanted the samples to fall according to. We then plug this into a new policy gradient algorithm, essentially the same framework as earlier. We run our current policy for m steps. We then estimate the empirical policy with maximum likelihood estimation. Essentially, we have a supervised learning problem to solve here. We then update our policy using our new sampling error corrected policy gradient estimate. And as before, we throw away our data and repeat. So I'm going to talk about 2 empirical results here, which I think are illustrative of some of the work. First, I want to show how sampling error relates to better, and correcting for sampling error relates to faster learning. So this is on the same grid world domain with discrete states and actions. The plot I'm showing here is going to show sampling error throughout learning. So the y-axis, higher means more sampling error, lower means less. So we'd ideally want to be low. And the x-axis is how long we've been learning. And if you just run a standard policy gradient method, you start with some sampling error, it tends to increase throughout learning, but then as the policy converges to an optimal one, sampling error decreases to close to 0. So now showing how this relates to policy improvement. So this is showing on the y-axis average return, so higher is better. This is what we're trying to maximize. And a Monte Carlo policy gradient method does this well, but if we correct sampling error, we do better. And what I find interesting is that we are correcting sampling error at where we see the most improvement is where sampling error is the highest here. The next thing I just want to discuss really quick is that probably the biggest limitation to this approach is that we need to solve a supervised learning problem in the inner loop of a reinforcement learning algorithm. So this has 2 disadvantages. One is that we're adding a computational cost to the algorithm. And the second disadvantage is that we're potentially adding many more hyperparameters to the algorithm, the right value for those hyperparameters might change from iteration to iteration. So one way to address this is to estimate the empirical policy using simpler policy representations than the target policy which actually generated the data. When we do this, we use a cart pole domain with continuous states and discrete actions. We train a neural network policy to maximize performance. And so what we do, I'm showing a diagram of the neural network we use, although this is a little smaller than the one used in the experiments that I report. We train the black connections of this neural network using policy gradient reinforcement learning. But we only train that we use the red connections, which are conditioning on an intermediate representation of the policy. We only train those to estimate the probabilities of the actions that we observed. So this is a much simpler supervised learning problem, and it makes it, this makes it our algorithm have less of a computational burden. So how this relates in practice is along the, this is again showing average return on the y-axis, and x-axis is how long we've spent learning. If we use a Monte Carlo style approach, this is how we learn. If we naively just train a whole separate neural network to approximate the empirical policy, we can do a little, though not significantly better in terms of how fast we learn. But if we use a much simpler form for the empirical policy, we can do much better and learn more robustly, quicker and more robustly. The idea of correcting sampling error has been looked at in other ways in the reinforcement learning literature. Probably the most closely related approaches are what we can call expectation methods, such as expected SARSA, tree backup methods, or expected policy gradient. These are methods which try to directly sum over all of the actions to avoid sampling in the action space. And of course, there's some other work outside of reinforcement learning and bandit algorithms, which also addresses the fact that Monte Carlo methods may suffer from sampling error and should be adjusted. So to conclude this part of the talk, my dissertation makes two contributions towards answering the question of how should a reinforcement learning agent weight off policy data. Contribution 3 of the dissertation was a family of regression importance sampling estimators that estimate the behavior policy instead of using the true one for importance sampling. Contribution 4 is the sampling error corrected policy gradient estimator, which improves policy gradient reinforcement learning. And there's additional results in the dissertation, both establishing the theoretical advantages of these methods, as well as additional empirical results. But in terms of answering our question of how should a reinforcement learning agent weight off policy data, the main takeaways from this part of the talk is that it is better to estimate the behavior policy than use the true behavior policy. And this is because doing so will correct sampling error in both policy value and policy gradient estimates. So I'm now going to talk, there's two other questions that this dissertation looked at. I'm going to talk more briefly about each of these, and then I'm going to conclude by discussing some directions for future work. So the other problem that my dissertation considered was how to use simulated data. And so I want to first point out that the problem of using simulated data, although traditionally has been studied separately from the problem of off-policy reinforcement learning, these are actually related problems. So in both cases, we're dealing with distribution shift in terms of what trajectories we observe. In off-policy learning, that's due to the policy which generates the data changing. But when we're using a simulator, it's due to this, the environment changing. Unfortunately, the environment of interest, we don't know the state transition probabilities for it. So all of the work that has been done for importance sampling, we can't actually do here. So we're going to need a different class of approaches. The algorithm that we introduce in my dissertation addresses this issue by using small amounts of real-world data to correct the simulation to produce, in effect, a better simulator. This work builds upon earlier work done at UT Austin, that is the grounded simulation learning framework. The basic idea is that if you can collect a small amount of real-world data, you can use that data to ground the simulator, meaning make it more realistic so that it produces similar trajectories to what you're observing in the real world. Once the simulator is grounded, you can apply reinforcement learning directly in simulation, but then your improved policy, you expect to improve performance when it's taken back to the real world. Whereas without the simulator grounding, we do not expect performance to improve. So this dissertation introduces the grounded action transformation algorithm that makes simulation more realistic by changing the actions passed in to the simulation. So first of all, I want to note here that we're not going to try to make every aspect of the simulation more realistic. If we were doing that, it would be more, we would be in the setting of model-based reinforcement learning, trying to just build a simulator of the world from scratch. What we're going to try to do is just make some aspects of the simulation more realistic. In the case of the experiments I'm going to talk about today, we're dealing with robot control. I'm trying to get robots to learn to do different tasks. And what we're going to focus on is making the joints of the robots move more realistically. So you can think of this as the policy is sending commands to each of the joints of the robots. These go into the simulator. The simulator updates a lot of different state variables, and then and including in those are the joint positions of the robot, and then these go back to the policy. So if we want to make things look more realistic to the policy, something has to change from when the policy sends its joint commands to the simulator and when it gets new joint positions back. And so our algorithm makes things more realistic by modifying the joint commands which are passed into the simulation. I'm going to talk only at a very high level about the algorithm, as I talked about it in more depth at proposal time. At a high level, what we do is our algorithm, the grounded action transformation algorithm, augments the simulation with what we call a grounding module. This grounding module takes the commands that the policy sends, modifies them in some way, such that the joint positions that the simulation sees at the next time step are more realistic. We show how this process the grounding module can be learned using two different supervised learning problems. We use a small amount of real-world data to learn to predict what would happen in the real world as an effect of the policy's actions. And then we just need to choose the action in simulation, which produces the same effect. So that's the high-level sketch of the algorithm. At the time of the thesis proposal, we had already applied this to the task of walking on the now robot. We started with an initial hand-coded walk that had been developed for robot soccer. This is a state-of-the-art walk. As far as we know, it was the fastest that anyone had got this walk to go before. We applied reinforcement learning using our algorithm entirely in simulation, and we ended up with the fastest walk that anyone had ever got on this robot. So that was at proposal time. I discussed that. Since then, we've done a couple of additional studies. So we looked at a task of trying to get the now robot to learn to move its arms to target positions. We used a simulator called Gazebo as a surrogate for the real world, and learned in a different simulator using that as the simulation. So on this task, I'm showing here final policy performance. The y-axis is how close the robot was learned to move its arms to the target position, so lower is better. And we see that by grounding the simulation, we were able to do a lot better than without providing this grounding. And so finally, I showed earlier that we were able to transfer a walking controller to the robot. Since the proposal, we also transferred a new type of walking controller. I'm not going to go into the details of this walk, but we used a simple linear function to generate a walking pattern on the robot. If you just optimize this linear controller directly in simulation, then the robot wasn't able to figure out how to get its feet off the ground to move forward. But once we grounded the simulation, the robot was able to make forward progress. So in terms of using simulated data, the fifth contribution of my dissertation was the grounded action transformation algorithm, which allows a reinforcement learning agent to learn from simulated data. And so also in the dissertation, there's some theoretical results on using an inaccurate model, as well as additional empirical results with the grounded action transformation algorithm. But the main takeaway in terms of how can a reinforcement learning agent use simulated data is that if we first ground the simulation using small amounts of data, it will lead to more accurate simulation, and we can do this by modifying the actions which are passed into the simulation. So I'm going to talk even more briefly about the final question that this dissertation addressed. I'm mainly going to just tell you what the contributions were. In terms of using both simulated and off-policy data, we looked at a problem of how do you place a confidence interval on the performance of an untested policy. We introduced two new algorithms which rely on a technique called statistical bootstrapping in order to develop these confidence intervals. And one of these algorithms makes use of using both off-policy and simulated data using a technique called control variance. So the main takeaway from these contributions is that by using statistical bootstrapping and control variance, we can tighten confidence intervals for policy value estimation as compared to previous methods in the literature. So this dissertation addressed the question of how can a reinforcement learning agent leverage both off-policy and simulated data to evaluate and improve upon the expected performance of the policy. We addressed this question by answering 4 smaller questions, and I'm going to summarize the answers to these questions. Off-policy learning can be preferable to on-policy learning if the behavior policy is chosen correctly. It is necessary to both correct distribution shift and sampling error in off-policy learning. And one way to do that is to estimate the behavior policy instead of using the true one for important sampling. Simulated data can be used if we first ground the simulator using a small amount of real-world data. And finally, combining simulated and off-policy data can tighten confidence intervals for high-confidence policy value estimation. Before wrapping up, I do want to talk briefly about 3 future directions for research that comes off of this, coming off of the work that I've talked about today. There's many more in the dissertation document that I'd be happy to talk about. The first of these is that the work I've done with using simulated data has assumed that the simulator models the target environment pretty well. So what if the simulator is only a very abstract model of the target environment? So consider if we wanted these simulated robots to learn to coordinate to play soccer together. But our simulator for the task was just a very coarse model of playing soccer, like these 2D robots passing the ball. So is it possible to use small amounts of experience from the true environment of interest to ground the very abstract model? And does doing so benefit learning in the target environment? The next direction, which I find really interesting, is how do we collect data for the new regression importance sampling estimator that I introduced. So I wasn't able to go into too much detail about it in the talk today, but we introduced a problem called behavior policy search, where how do you select the behavior policy for importance sampling? And kind of the answer to this was you basically want to increase the probability of seeing trajectories which are rare under the evaluation policy and lead to some high magnitude sum of rewards. So the question is this better behavior policy for ordinary importance sampling, the same for regression importance sampling? I would argue that it likely is not a better behavior policy for regression importance sampling. I don't have time to talk about some preliminary empirical results on this. I have some discussion about it in the dissertation document. But what I believe a good behavior policy would be needs to actually experience new trajectories that it hasn't seen before. And the final direction for future work that I want to look at is how can we apply what we've done for policy value estimation to the problem of policy evaluation, or learning a value function. So a value function, for those of you who may be unfamiliar, for any state, it tells us how much reward should we expect to receive if we run, how much cumulative reward we should expect to receive when we run our fixed evaluation policy. Value function methods typically learn in an incremental fashion, where they're moving towards an estimate of the value of the policy at a particular state. So I'm showing that as this target use of t here. So one definition of the target use of t would have a off-policy correction if we were an importance weight, if we were generating the data in an off-policy fashion. So to the contribution of this dissertation, is there a way that they can improve the use of importance sampling for value function learning? So for collecting data, what is the right behavior, the optimal behavior policy if our optimal, as our value function is changing during learning? Or what if we have different evaluation policies that we would like to evaluate at the same time? And then for weighting data, how can we estimate the behavior policy if we're doing online value function learning? Or more importantly, how do we correct sampling error in value function learning? So before wrapping up, I want to thank my collaborators, in particular those who've been very involved with the work that went into my dissertation. Of course, Peter's been involved with everything. Scott's been involved with a lot of this work. And then Phil Thomas and Chung Gu were really involved with the work on behavior policy search. So with that, thank you all for your attention and coming to the defense, and I'm now happy to take questions.